Hi, I'm Randall Heyman, a mathematics academic. Welcome to my Corona Help playlists where I do quick turnaround videos to help educators and students. If you'd like me to make a video for you, be it at primary school, secondary school or university level, then comment me below any of my videos or drop me an email at coronahelpmathematics@gmail.com. Okay, so today we are going to do open and closed sets, an incredibly important idea in analysis, and I can explain it just using the idea of boundary points that we did in the last video. So let's start with a definition. Let me just make sure I get it correct. Yeah, this is the best one. Definition. A set is closed. Is open. Let's say open to. Let's do open first. If it contains none. So the important word here is none of its boundary points. Open contains none, and a set is closed if it contains all of its boundary points. Okay, so let's just note open is not the opposite of closed. So let's do an example. I'll show you, I'll give you, this illustrates the point well. The set R in the metric space R with D, the normal D of AB is equal to the absolute value of A minus B. So this is just the standard, stock standard real, but the set we're talking about is actually the real number line itself. So this set R is both open and closed. And the reason for that is that it's got no, it actually has no, there are no boundary points. So it satisfies both conditions. Okay, now there is an alternative definition, and often at university you'll have to prove that this definition is valid, is correct from the, so you prove definition 2 from the first definition. So a set S is open if and only if about every point of S there is a ball you might think there exists a ball, so we can change the radius as we see fit, but there must be at least one ball completely contained in S. There's also a definition, a similar sort of definition 2 for a closed set, but it requires the concept of accumulation points, which I don't want to get into at this point. I may come back to that if necessary. Okay, so let's do an example. So let's let S be the set XY such that X squared plus Y squared is less than or equal to 1. So I'm going to draw that so we can see it. Let's draw it, we want a circle about there. And let's put an axis on it. And let's put an axis the other way. So about there, about there. Not that good. I'll get better. Y, X, 1, 1. Okay, so the important point here is that this is, it's everything inside this unit, with a unit circle we call it. Now, we can actually, if we're going to work out whether this is open or closed, it's useful to know what the boundary points are. And the point is that the boundary points are independent of whether the set's open or closed. So I don't have to know that first. I can just work out the boundary points directly. Boundary points, remember this is what we covered in the previous video, boundary points of S. So let's discuss that, equals. Okay, so the idea is that we're looking for a point, and I'll give you an example of one. This point here, right on the line. If I draw a ball around it, in fact, every ball that I put around it, doesn't matter how big the radius, then there'll be some point. There'll be at least one point that's inside S. Here's one point that's inside S, and there'll be one point that's outside S. Here's a point that's outside S. So this is a boundary point, and in fact every point on the line will be a boundary point. So let's do it in blue. This point's a boundary point, this point's a boundary point. Is this point a boundary point? Well, no, because I can construct a ball and there's no point in that ball that is in S. Is this a boundary point? No, because if I construct a ball, there's no point that's outside S in that ball. So the boundary, we know exactly the boundary points of S. It's the set of points x, y, such that x squared plus y squared equals 1. So now we look at this and we say, does S contain its boundary points? All of them? Yes. So S contains all of its boundary points. So S is closed, or if you want, or a closed set, you could say, closed. Let's try and spell this correctly, or a closed set. Good. Okay, let's now change the problem. Let's look at a different set now. I'm going to be a little bit cheeky and just rub out, oh, not doing this too well this time, run out some points. And now I'll draw in, so it's a dotted line now, which means that we don't include that line in S. Okay, so I'll change the definition of S up here. I'm going to just get rid of that equals to. It's strictly less than 1 now. Okay, so the boundary points, which I mentioned this before, important point, the boundary points don't change. This is still true. This is still the boundary points of S, even though I've changed S. But now if we go over to the left, S contains, let's just change this, none of its boundary points. So S is open. Or if you want, we could say it's an open set. And just to finish up, I just thought we would look at this up here, definition 2. A set is open if and only if about every point of S, there is a ball completely contained in S. So what this is saying is if we take, this is an example here, this one here, this is a point in S, and around it we can construct a ball and the entire part of the ball is in S. So that's one point. Now we have to be able to do that for every point in S, but I think you can see that that's the case. Even if I get very close, I can't, well actually, what I can do is, here's a point that's very close to the border. But if I now go like this, I wonder how much I can do this. What is that? 500%, okay. You can see that I can actually draw a little circle around that. And that circle is completely within S. So if I now go back to 100%, or close to it, whoop, hard to get. You can see that around every ball, we just did that one there, but around every ball, around every point in S, we can construct a ball, and the entire ball is in S. So that shows us again that S is open. So that's all I wanted to say about open and closed sets at this stage. Incredibly important concepts though, open and closed sets. It's very important you understand them if you're going to go on and do more things in an analysis. So I think in the next video, I'll probably do some harder examples. But if you've got any questions on what I've done now, now's a really good time to comment me or email me at coronahelpmathematics@gmail.com. Say you don't understand, because if you don't get this, it's going to be very hard going forward to understand more analysis.